Hello students, now let us see about the linear block codes. So already I said to you regarding the channel coding theorem, that is channel encoder at the transmission side in the digital communication. So here we are using linear block codes to generate those redundancy bits. So block codes which exhibit linear property are called as linear block codes. Example are Hamming code, cyclic code, BCH codes, etc. So remember that in all these code generations, we are going to use modulo 2 addition, that is XOR operation. That means when the inputs are same, the output is 0, and when the inputs are different, the outputs are going to be 1. Now let us see in detail about this linear block codes. So as you have already seen the introduction part of the channel encoder, that is, we are going to have k number of message bits that you are sending into channel encoder. So the output you are going to get k bits plus q bits, where q will be is equal to n minus k. Now let us consider m, which is given by m1, m2 and so on up to mk, where k is nothing but the number of message bits. Now c is nothing but c1, c2 and so on up to cq, where q represents the check bits. So if you go for your systematic code, so as I already said to you, your message and your check bits both can be separated. That is, we can able to identify which are my message bits and which are my check bits. Now let us see how we can able to generate the check bits by using this block codes or the linear block codes. Now all the thing what you have to do is, you need one generator matrix to generate those check bits or to generate the entire code word. So code word is nothing but n. N is nothing but the total code word, which is given by k plus q, where k represents the number of message bits and q represents the number of redundancy bits which you are using. So x is equal to mg, where m is nothing but the message bit and g is nothing but the generator matrix. Now by using this generator matrix only, you are going to generate the code words. So x will be equal to, that is the order of this x will be equal to 1 cross n, where the order of this message bits will be, matrix will be 1 cross k, and the generator matrix will be of k cross n. So n represents the total code word, k represents the number of message bits. Now see here, the generator matrix is given by, that is the generator matrix will be in the form of I and p. I is of the order of k cross k and p is of the order of k cross q, where I represents the identity matrix and p represents the submatrix. So totally the generator matrix is of the order of k cross n. See the matrix of p, p11, p12 and so on up to p1n and so on at the column wise pn1, n2 and so on up to pnn. So check bits are calculated, that is the redundancy bits are calculated as matrix multiplied with your submatrix. So this is the formula for generating the check bits. This is a formula for generating the check bits. Now let us see in detail, that is let us consider an example first. So the example is, find all the code vectors of the code given the generator matrix. So generator matrix was given, so which is of the order of rows into columns, right? So 3 into 6. So your generator matrix, as I already said to you, it is of the order of k cross n. So here the generator matrix of the order of 3 cross 6, that means the k value is equal to 3 and n value is equal to 6. So 3 bits, that is they are the message bits. So the possibility of messages are 000 to 111. Now you have to identify in the given generator matrix which is my identity matrix and which is my submatrix as given. So you have to remember this formula, that is I is nothing but k cross k, that is here the k value is 3, so I will be of 3 cross 3, that is first 3 rows and 3 columns will be of your identity matrix 1 0 0 0 1 0 0, and remaining it will be of your submatrix. So I, which is nothing but 3 cross 3, and P is nothing but k cross q, which is equal to 3 cross 3. So identify the submatrix. Now this is my submatrix. Now how we are going to find out the check bits? C will be is equal to m into p. So for the message bits will be of from 000 to 111. So consider my first message signal 000 into the submatrix. So after doing the multiplication of that, I got finally the resultant value is 0, 0, 0, 0. That is, see that row multiplied with column 0 into 1 plus 0 into 0 plus 0 into 1. So here you can't go for the plus, you have to go for your XOR operation. So accordingly, we have got the value as 0, 0, 0. So for the message bit of 000, the check bits generated are 0, 0, 0. So like that, you have to calculate for the remaining messages also. See here, 0, 0, 1 into the submatrix. I got as 1, 0, 1 till 111. So for all the 8 message bits, you have to do it. So finally, we have to create one table which shows the message vector and the check bits. See that for the message bits vector of 000, I got the check bits as 000. So as I have said earlier, see there, I have calculated it as 000 for the message bit of 3 zeros. Next, what is my next message? The next message is 001. So I have calculated it. It is of 101. So in the similar way, you calculate for the remaining messages. So I have to write all the check bits for all the possible messages. Now if you combine this message vector plus your check bits, that is going to become your code vector. So individually we call this as your code word, and group of all these we call it as a code vector. Now we need to find out the weight of the code. So weight of the code is nothing but number of non-zero elements in the each code word. Now if you look at here, the first one all zeros. So weight of the code is 0. Now if you look at here, number of non-zero elements were 3. So the weight is 3. Here it is 3 again. Here it is 4. Here it is 2, and so on. Like that we have to write the weight of the code. Next, Hamming distance. Hamming distance is nothing but compare these two code words and see how many 0 to 1 transitions and 1 to 0 transitions were there. Based upon that, I have written this Hamming distance. So you will be comparing. So when you come for the last one, you will not have anything to compare. So go for the first, you will be getting your Hamming distance as 4. See here, 1, 1, 1, 0, 1, 0. So compare with your previous one, so you will be having your 4. So the minimum distance which you get here is your 3. So this is called as your Hamming distance. So Hamming distance, minimum distance, which is given by 3. Now let us see what is your error detection capability for your linear block codes. So D minimum is greater than or equal to S plus 1. So D minimum we have calculated from here the Hamming distance, which is nothing but 3. So 3 is greater than or equal to S plus 1. From that 2 is greater than or equal to S, that is S is less than or equal to 2. And see for the error correction capability, D minimum is greater than or equal to 2t plus 1. So from that I got the value as t will be less than or equal to 1. So this is regarding the transmission side, that is your message bits, you have added your redundancy bits, and you have generated the code vectors. So this is related to your transmission side. In the same way, we can also use the Hamming bits or the Hamming code, so which is given by H will be equal to, that is, this is the H. So parity check matrix and your generator matrix both were related. So both are related. See there, once if you know the generator matrix, automatically you can find out what is your parity check matrix also. So H, Q cross N, P transpose and I. So you will be getting from the generator matrix, so you can find out the P transpose of that, and identity matrix you can know it already. So identify P transpose and I matrix. P transpose you convert it to P, then automatically your codes will be generated. So this is my H, this is my H, that is H parity check matrix Q cross N. Now this is the block diagram. So input bits here M1, M2 and so on, these are the message. So I have written the subscript as K, and here it is nothing but the check bits C1, C2 and so on up to CQ. So all are XOR operations. So to each XOR operations, all the message bits were connected. All the message bits are connected to all these XOR operations, and finally these are the output code words which you are going to get. So once again,